So today we'll look at another way to calculate delta H. So this one is going to be involved with chemical reactions still, but we're going to look at, there is inherently a energy associated with formation of a chemical, and those will be published in most chem textbooks. You could certainly use Google to look those up also in a table. And so we'll check that out today. We're going to use this equation, and it's in your equation sheet, and it looks a little intimidating, but it's not. Delta H for the reaction, and those little postscripts, the superscripts that are the zeros there, just means standard state. So in the back of the textbooks, it'll tell you what standard state is, but we're going to assume all these questions are going to be in standard state today. And it says it equals sigma delta H formation of products minus sigma delta H formation of reactants. And all that means is summation. We're going to have to add up all the product delta H values that we get from the textbook and subtract them from all the reactant formation values. Now we certainly also have to take into account any coefficients that are involved in the chemical reaction. So we'll practice a couple of those. So there is a definition of delta H formation, but we'll kind of examine that a little closer here. So down below, I gave you an example of what a formation reaction would be. And a formation reaction is nothing but the elemental in their standard states, whatever those chemicals would have to be, those elements would have to be, and combining to make whatever chemical we're making, in this case glucose. One thing that's going to be of importance for sure is this. If it is a pure elemental in its standard state, it is already formed. It doesn't take any energy to already form it. So that value would be 0. So where's that going to be important? Sometimes the textbooks will skip some of those elementals. You won't be able to find them. Or on a test, I may not give you that the delta H value for solid carbon. You're supposed to know that the delta H for that, the formation is 0. Elementals that are diatomic molecules, the same thing. So the value for hydrogen gas or oxygen gas, you may or may not be able to find them in textbooks or on the tables that would be provided on tests, but those values for delta H formation are 0. Okay? But anyhow, if you were going to form glucose, you would need to form it from its elementals. So we'll give a couple of these. Actually, I think if we just give one of these a shot, I think it's going to be pretty self-explanatory about the rest of these. So let's do the more difficult one here, aluminum nitrate. So if we were going to form aluminum nitrate, and by the way, we don't always need to use these designations of solids, liquids, and gases, but for this section, it's going to be very important, because when you go to the back of the book and you're finding something like H2O liquid, it will have a value. But the H2O gas, to form that, will have a completely different value, or H2O solid will also have a different value. So you need to make sure you designate solid, liquid, or gas. So in this case, we're doing the aluminum nitrate. So we would need to have, it doesn't really matter where you're sticking these on the left-hand side here, but I'll kind of try to stay with the same sequence as aluminum nitrate. So you would need aluminum, and that's in the standard state as a solid. By the way, all metals are solids at room temperature, except you're going to have to know mercury is a liquid. nitrogen gas, and oxygen gas. And I don't think that's balanced. And by the way, we haven't ever seen this before until now. You are always making, make a better one there, you're always making one of the products. So therefore, when you go over on the left hand side and add coefficients, you will often see fractions, and that is okay. So like, just to give you an example, I said I was only going to do one of these, but let's do water. So you need hydrogen gas, and you need oxygen gas. And again, you're always making one, and no one puts the ones there, but I'm going to put the one in here for the time being. And that would be one hydrogen gas, but you would need a half of an oxygen gas. Now, yes, that's impossible to actually have a half of a molecule, but the way that these are always written are to make one of the products. Okay, so looks like we have one aluminum. Okay. But right now it looks like you need 3 nitrogens, but it's N2. So you could go 3 halves. That would work. And you get the idea. So you'd have to do, I guess you could go 9 halves over here. If you want to put them in that type of fraction, that's perfect. If you want to do a whole number with a fraction, that's okay too. Okay, so if you remember correctly, earlier I said that elementals in their standard state have delta H formation values of 0. So which ones do not have a value of 0? Something that's not in its elemental state. Well, water, first of all, isn't an element, so it would not have a value of 0. Mercury is typically a liquid, not a solid, so it would have to be formed, so therefore there's an energy involved with that. The halogens, by the way, the top halogen, fluorine is a gas, chlorine is a gas, whoops. Bromine is barely a liquid, but it's a liquid, and then iodine is a solid. So that's in its elemental state. And of course, here's another molecule that sneaks in here. So that cannot be an elemental. The rest of those, elemental in its standard state, elemental in its standard state, elemental in its standard state. Okay, so we haven't really had to use the textbook for any of these sections yet, but you do need to use a table that has delta H formation values. So in your textbook, it's Appendix 3, page A8. If you would want to use Google, that would be fine. But if you're trying to check answers with the back of the book, for example, occasionally there might be a number that could be slightly different. Maybe some of these numbers aren't completely acceptable. There's not a uniform number. They might be slightly different. On a test, I will give you a table and you'll use those numbers. So to do the following, we're going to try to use the textbook. And this would be a typical question. So if you remember correctly, the equation is the summation of all the products. So let's do the products first. So we'd have to go back to the back of the book and find carbon dioxide gas, not liquid, not solid, but gas. And then we'd find water's value as a gas, but multiply it by 2 because there's a coefficient of 2. Those be all the products. We'd add all those up and then subtract all of the reactants. and then that would give us the delta H for the entire reaction. And remember, I told you that often people do not designate these things, but RXN is the reaction, delta H reaction. Okay, so let's jump in. So I go to the back of the book and I find carbon dioxide, and it has a value of negative 393.5 kilojoules per mole. Now, because all these are going to be kilojoules per mole, I'm not going to bother writing kilojoules per mole except for when I'm into the answer. So that is carbon dioxide's value. Add it to any of the other values. Well, we also have 2 waters, and I guess it's also a gas, so make sure you're very careful with that. And that value is negative 241.8. Okay, so there's all of our products. You add those up and then subtract any reactants. And in the back of the book, they take the organics and they put them in a separate section. So if you're looking alphabetical for CH4, you're not going to find it. You have to go to the organics for that. And the value for that one is negative 74.85. And then I don't even have to look at that value because that's an elemental in its standard state. So that's going to give me a value of 0. So if I add all those up, I'll have my answer. Now, let's talk about this for a second. We should have some ideas. This is a combustion reaction. Combustion reactions are always exothermic. So when we do all this summation, we should have a negative answer. If we don't, then we know we made a mistake somewhere in our with our calculator, or with losing a sign somewhere along the line. And when I do this, I get a value. And by the way, I would stay with the decimal places that are involved with what's in the back of the book. Not really significant figures in this case, and I certainly wouldn't be taking points off unless you just lopped off all these decimal places. These are not experimental. This isn't experimental data. This is, we're going to call these true values. So we're not going to try to concentrate on significant figures with this. So that time we solved for the delta H for the reaction. But you could also be given the delta H for the reaction and then solve for maybe one of these individual parts instead. And that's what we'll do for this next one. So the delta H again is given to us for the reaction, but what's not given to us is the formation value of isopropyl alcohol. So we're going to look up all the values for the other items, and we have the delta H reaction, and with that we can conclude what isopropyl alcohol, its formation value would be. So we have a delta H already for the entire reaction, and these are all in kilojoules per mole again. Even though that doesn't say kilojoules per mole, those are all kilojoules per mole. And then I'm going to find all the products. So we had already looked those up from the previous question. CO2 has a value of negative 393.5. And remember, there's 6 of them. And then there are 8 of the gaseous waters at negative 241.8. Okay, and then we have to subtract it from all of the reactants. Well, we don't know the isopropyl alcohol, so I'm just going to get the variable X. And we also know that oxygen gas in its elemental state has a formation value of 0. So now we have everything we need to solve for that part. So I guess what might be easy for you guys would be to add this all up. and then get everything over to the negative 4011 kilojoules per mole side and divide by 2 to solve for X. And when I solve for X, I got a value of negative 142.2 kilojoules per mole. So that is the delta H formation. And this is, again, we're always assuming for this unit, for this section, standard state. Because if it wasn't standard state, 1 atmosphere and 25 degrees Celsius, these values would not work. So that's the delta H formation for isopropyl alcohol. Okay. And our last question has a little bit to do with delta H formation values, but it also ties in many of the other things we've had so far in Unit 6. So this is a chemical reaction. Magnesium oxide, by the way, a very, very typical reaction that a lot of people do in AP chemistry around the country. Magnesium oxide plus 2 H positive. H positive in this case is going to be hydrochloric acid, but you don't have to use hydrochloric acid, but that's the typical acid that people use for this. They carry out the chemical reaction in a polystyrene cup. For us, it's a coffee cup calorimeter. That's pretty typical. And they decided to do 4 trials of this. Okay, so they measured the amount of hydrochloric acid, they measured the grams of magnesium oxide they're using, and they got initial and final temperatures. So our first question has nothing to do with thermochem at all. It's stoichiometry. What's the limiting reactant? So we were given a molarity and a volume, and we were given a mass. So we need, and we were also given a 1:2 ratio between the 2 chemicals. So we can use both of those things to figure out the moles of the 2 reactants and see which one runs out first. I'm probably not going to do a lot of the math because the math is pretty well spelled out in our answers here. So I'm going to go back and forth between these 2. Okay, so they determined that there is 0.1 moles of hydrochloric acid, but there is a 10-fold difference between the magnesium oxide and the hydrochloric acid. Even though it's a 1:2 ratio between the 2 chemicals, definitely the magnesium oxide is going to run out much earlier than the hydrochloric acid. So the magnesium oxide is the limiting reactant. So how did they get the point for this? One, they had to do a little bit of math and then analyze that math. By the way, you could have actually done this without math, but I'm not going to recommend that for future questions. But you could have gotten away with no math on this particular part A here. But we're going to need those limiting reactant moles anyhow, so it's probably a good habit for you guys to do the way that it's described in this first part here. So let's jump back and forth between answers and questions. The data in one of the trials is inconsistent with the data in the other 3. So it's basically saying someone screwed up somehow in one of the 4 trials. Identify the trial that's inconsistent and draw a line through that data. Okay, so let's erase the things I already had up there. Okay, so we've already determined that it's the limiting reactant magnesium oxide, right? So that's going to drive the temperature changes when you're thinking about the Q equals Cm delta T. So if you use a little bit of stuff, 0.25 grams, you should get the same exact little bit of delta T. Well, with the first one, you get 25.5 goes up to 26.5. That's a difference of 1.0 degrees Celsius. But the trial 3, now you get 2.1 degrees Celsius. Well, that's not consistent. You should get the identical same amount of delta T. So now we're down to, is it trial 1 or trial 3? Well, with trial 2 and trial 4, you double the amount of aluminum reactant. So that means you should be able to double the delta T, because those are proportional with each other, directly proportional. So it looks like with trial 2, there is a change of 4.1. That's about double of 2.1. And then trial 4, it's 4. Now remember, this is all experimental, so they're not going to be perfectly a change of double or whatever. But it certainly now looks like trial 1 is not consistent, because it doesn't go by that same change of delta T that you'd expect with that you get with trial 2, trial 3, and trial 4. And we can look at the answers later on, but I believe that's gonna be what they mention. For parts C and D, use the data from one of the other 3 trials. So we've already canceled out trial 1, so we're not going to use that. I think I'm just going to use trial 2 to do all the other work, but there's no reason why you couldn't use trial 3 or trial 4. Assume that the calorimeter has a negligible heat capacity, meaning that we're not going to worry about C-cal in this one, and that the specific heat of the contents in the calorimeter is 4.18. And we're typically going to assume that because this is mostly water with the salt, with a little bit of solute, that we're going to have the specific heat of water. And then we also have the density of the solution as being 1 gram per milliliter, and we're always going to assume that unless told to us otherwise. So part C is calculate Q. So we need a C, we need an M, and we need a delta T. So I think the C was given. The M is going to be all the things that are in the calorimeter. So what's in the calorimeter? There is 100 milliliters of hydrochloric acid, meaning there's 100 grams. But what else is in the calorimeter that the thermometer can actually touch? I'm looking at trial 2. There's also 0.5 grams of magnesium oxide that gets incorporated into that. So the mass, this is a little bit tricky, is 100.5 grams. And then the delta T is pretty well spelled out, 29.1 minus 25. So we can look at an answer here. Okay, so again, I said that you could have done any of these trials. I did trial 2. So here's our 100 grams. Here's our 0.5 grams. Here's our specific heat, and here's our delta T. So we're going to eventually want to get that into a kilojoules, but there's no reason why you couldn't have reported that in joules, unless it tells you in the question that it needs to be in kilojoules. Okay, so now we're into part D, and this is typical. So in part C, calculate Q. Part D now, calculate delta H. So delta H, remember that delta H is Q divided by the limiting reactant moles. Okay, and we had already figured out what the limiting reactant moles were. So let's go back. Answers. So we'll talk about the sign in a second. So we had the 1.7 kilojoules. Whoops. The 1.7 kilojoules, because I did trial 2. So moles of limited reactant, we'd already determined what that was, but they did it again. And then there's our joules, but we had the 1.7 kilojoules. They just converted that again here. So they get 140 kilojoules per mole. But why is it negative? Because we didn't have a negative up here. Remember that the calorimeter is the surroundings. So the surroundings gained heat. That's why the temperature of the water went up. But we're not interested in the surroundings with the delta H. We're interested in the system. So that means that if the surroundings gained heat, the system lost heat. And that's where the negative comes in. Okay, so don't forget that. So kind of a couple places to kind of make sure you think about is that negative there, and not forgetting to incorporate that other reactant that gets incorporated into the entire mass of the calorimeter. And we're almost done here. Part E, now this is why I put this in this section. Enthalpy of formations are given, and this is very typical about how it would be on the test. Here is a little table, not the textbook, but a little bit of table, and then you are to determine the formation of well, not the formation. The formations are given. You are determining the delta H of that reaction. Now, when you do it with the delta H formation values, we're going to assume that is a theoretical true value. And then when we're doing it with trials in the lab, that's experimental. So we have an experimental answer already that we got in part D, but now in this next section, part E, we are doing that same thing, but theoretically. So let's go look at their work. Okay, so the formation equation, take all the products, subtract them from all the reactants. Don't forget about coefficients. And the only coefficient in this particular one is with the H positive. And remember that, well, not remember. You don't have to remember anything in this case. You just have to be able to look at the table, and it gives you a value of 0 for the H positive. Whoops. Okay, so when they did all that addition, subtraction, they got a negative 151 kilojoules per mole. So that, again, is, we can call that theoretical or true. And then we are going to eventually want to compare that with, let me erase a little bit of this here. We are going to want to relate that to this experimental. So experimentally, negative 140 kilojoules per mole. True, 151. So we did not get all the heat. We did not account for all the heat that we should have. So I think we're probably going to have to, we're going to have to address that in this last question. The accepted value and the experimental value do not agree. If the calorimeter leaked heat energy to the environment, would this help to account for that? And yes. So when we went and did the Q equals Cm delta T, we did not account for the Ccal. If we would have accounted for the Ccal, our Q would have been bigger, then our delta H would have been bigger, and then it might have been closer to that value of 151, negative 151 that we should have gotten. And I think in part F it talks about that. Okay, so that's it for today.